Hello physics students, welcome to video 2 in circular motion. In this case we're going to quickly look at the formulas and the calculations. So let's get to it. Now this is looking at a circular motion. We're looking down on an object that's going around in circular motion, and we have 2 points A and B, and at point A we can say that it has velocity 1, and at point B it has velocity 2. Now we could call this the initial velocity and label that as U, and this is V. Makes no difference, it's just the nomenclature. And in this case it's going around in an arc like this. Now that means that we're given if we wanted to find the change in velocity, we would do V2 minus V1, and notice the direction of V1. Now of course, because we're subtracting vectors, we actually need to add the negative of that vector, and therefore V1 becomes minus V1, and we end up with this resultant triangle joining them head to tail, and this therefore would be delta V, the change in velocity, and we get that from this equation here. Now notice that, now let's do some drawing. Notice the direction of delta V, because delta V will tell us the direction of the force, because if we remember, we have acceleration equals V squared on R, but we also have acceleration equals delta V on T. Alright, now notice I use the subscript to denote that I'm working out the centripetal acceleration, and you'll see that on your formula sheet. It's a good habit to get into, just to avoid confusion. Now the point of writing these two is, in both cases, the only thing that in both cases you have a vector quantity and you have a scalar quantity. The velocity is a vector quantity because it has a direction and a magnitude, whereas the time and the radius are both scalar quantities. The radius could be in any direction and the time is just time. And therefore it is the change in velocity that determines the direction of the vector quantity, which is the centripetal acceleration. And in this case, because of the direction of V1 and V2, the resultant is in this direction. And that would mean that for this time interval that we're looking at here, this would be the direction of delta V. Now that seems a little bit confusing. Oops, oh no, I just hid my ink. Let's just change, I was just trying to change the color here. I've lost it. It's back. So I'm just trying to change the color, and so from here to here, this is the change in delta V. Now that might seem a bit weird in terms of the direction, but that is the actual direction, because it's very important to recognize that the centripetal acceleration, this direction, must always be towards the center of the circle. So we could also label this arrow as AC, and that leads on because we have FC equals MAC. And because mass is also a scalar quantity, the direction of the centripetal acceleration gives us the direction of the centripetal force. And if I can just change my color again, alright, we should see that the centripetal force in this case is towards the center of the circle, which is what I told you before. The centripetal force is always acting towards the center of the circle. Now if we were to shrink this time interval down and B was there instead of way up where it is here, we would see that as we reduce the difference between V1 and V2, the centripetal acceleration is always towards the center of the circle, and the centripetal force is always towards the center of the circle. So if we picked any point in this circle, we would have the same magnitude of centripetal acceleration, but we would also have the same magnitude, would have a different value because it's a different calculation, but the same magnitude in each of these cases of the centripetal acceleration. Because this body is moving with a constantly changing velocity, it is accelerating, but the acceleration is only causing a change in direction. Let's get rid of all that now. Okay, I think we're right there. Okay, and it just says that. So you need to be careful about that, and you also just need to follow what we're doing there. Now the equations of motion, we just described the first one, AC equals V squared on R. Now since F equals ma, we can substitute in this value for A, and we get FC equals mv squared on R. And because we can tell this is, of course, that's the circumference of a circle. Alright, so if we're talking about circular motion, this is the period, and so the time it takes to go one complete circle, it covers the circumference of the circle, and so that's the displacement, and t is the period. That's where that comes from. And now we could substitute this into here, and we would end up with these two equations. We actually substituted in here as well, and the first one is AC, the centripetal acceleration, equals 4 pi squared r on t squared, the period, and the centripetal force equals m 4 pi squared r on t squared. Looks a bit complicated, but it's actually already derived for you, and it's on your information sheet. Now students just need to be aware of these squares. The number of students that forget to do these squares when they're doing these calculations would astound you. So try not to forget, because you won't get the right answer. Let's do an example. In this case we have a motorcycle and a rider with a total mass of 1,250 kilograms travelling on a circular track, which is fortunate, and we're really only ever going to do circular tracks or corners that are circular. So we have a radius and we have a velocity. So because some of us are beginning to do physics for the first time, what I like to do is circle the information. So there's something, and there's something. Now, some of the information given in a question might actually not be necessary, but some of it will be. So you are always given enough information to answer the question, and so you need to just be on the lookout for that. And then I like to, when we're beginning out, to just assign letters to what we're given. So that would be R, we've got the mass, and we've got a constant for speed, so we can call that V, because we're talking about circular motion. Over here we're actually told what we want to find. We want to find AC, the centripetal acceleration, FC, the centripetal force, excuse me, and capital T or T, time. And that's what we're trying to find. So we're given enough information and we just work our way through it using the equations that we're given. Let's have a go. Now it's already worked out for us. And so we would recognize to find the centripetal acceleration, we use AC equals V squared on R, put the numbers in, and we get the answer. Voila! Same with centripetal force. Find the equation, and notice that this M is put on the outside. Sometimes it's written, I think it's on your formula sheet, is written above the divider. Doesn't matter mathematically which way you do it, entirely up to you. And again, we get our answer. Being careful to ascribe the correct units. Now, notice also that there's not a direction because we're doing with a centripetal acceleration. It's pretty much a given that it's towards the center of the circle, but it doesn't necessarily have any harm in writing its direction, just to verify to whoever's looking at your work that you know the direction that each of these quantities is going in. And the time taken is they've rearranged the equation and they put it in and they get the right time. There you go. Here's another one. A car is driven around a roundabout. We've given a speed which is conveniently converted into meters per second, but sometimes that won't be. You need to remember how to convert kilometers per hour into meters per second. That's just a given. We've got the radius and we've got the mass, and we're trying to find pretty much the same things. In this case, they actually ask for the direction, so make sure you're explicit and you do give a direction. Putting the numbers in, you get the answer. Now these guys, when this is from a textbook which they try and encourage people to put the units in their equation. I'm not necessarily a big fan of that because the units often get in the way, and it's just making a bit more work for you. What you do need to recognize though is what the units of the answer are, and you need to make sure you're aware of that. And in this case they state the answer 9 meters per second to the minus 2 and the direction towards the center of the roundabout. And what's next? To find the magnitude and direction of the force. Now I've noticed that there's two possible ways of doing it. You can substitute it into our formula F equals ma, and because we've just worked out A, and we get the force, or you can use the equation F equals mv squared on R, which is our centripetal force equation. Notice they use net. That's just the way this textbook uses. Don't get confused by that. I'd much rather prefer, if you're talking about circular motion, that you would label it as centripetal force, because that's what it is. Yep. And they put the numbers in, being careful not to miss the square. Now, just another little example, but a little bit of preamble beforehand. A gravitron. Some of you may have been on a gravitron. It's a ride that you go in some fairs and theme parks and things they might have. You can experience up to 4 Gs on it. The outside looks like that. I don't think they've had one at the Launceston show for a while, but it can occasionally tour. And inside, basically, it's a big circular disc that you walk into and you lean up against this wall, and it spins it round faster and faster, and you get pushed up against the wall, and you've experienced quite a few Gs, 4 Gs. Nothing to be sneezed at. Alright, that's the context, so let's have a look at the question. We've got an amusement park ride. This guy's on it. It's 3.5 meter radius. The rate of rotation is every 2.5 seconds, so that's a little bit different. Excuse me. We have to work out the acceleration, the net force, and then draw a diagram. Now, students often don't like drawing diagrams because it means they actually have to visualize what they're doing. So it's good practice drawing diagrams because it reaffirms that you're actually understanding what you're doing. Now, first thing is, what are you given? You're given the mass. So I should have gone through this and circled the information, but in this case they've labelled it for us. We've got the mass, we've got the radius, and we've got the period because it is one rotation every 2.5 seconds, and that's the definition of a period. Put the numbers in, being careful of the square, and we get the answer and the direction as given. And again, we could use F equals ma or Fc equals m4 pi squared r on t squared. Put the numbers in, and you should get the right answer, obviously towards the center of the circle. And lastly, the diagram. Here's our student, and we've worked out the centripetal force, which is 1.3 times by 10 to the 3 newtons. Has a weight force of 600 newtons, let's not forget that. Has a friction force acting against it because the person's not sliding up or down. I forgot to mention, what they do is they spin you round and you're standing on a platform, and as it gets faster and faster, the floor that you're standing on pulls away from you, and so you're just pinned against the side. And that's why in this case you've got to have a friction force of 600 newtons so you don't slide down. When it slows down, you either slide down the side or the floor comes back up. I think I went on one once when I was a kid, but a long time ago. Whoops. Now notice they've also labelled a normal reaction force for the wall, which is equal to the centripetal force, because the centripetal force is making you go around a circle, and what's providing that centripetal force is the wall pushing. So it's not saying that you're experiencing twice that amount of force. It's saying that the net force, the reaction force of the wall, and the centripetal force are the one and the same, acting in the same direction with the same magnitude. How's that sound? That's enough, I think. So in the next video I'm just going to talk about some applications of circulation. Cheerio!